If you don't, it's okay by me. Okay? And I've had 2 or 3 graduate students that they really want me to give them a deadline. But that's not the way I operate. Okay? I mean, you're here to learn to be a professional, and you should act like a professional. My father taught me when I was 5 years old, if you're old enough to be an adult, you should act like an adult. And he held me to that standard when I was 5 years old. Okay? My older brother didn't do so well to that standard. He had fights with my father, but I found it was just easier to get it done. In fact, the way I learned not to procrastinate, he used to say to my older brother, well, have you finished such and such, some assignment he'd given him? And my brother would say no, and he'd get upset with him. And when I was about 7 or 8, he would come to me and he'd do the same thing. Have you finished such and such? I said, yep, all done. And he would never congratulate me or anything. But I could tell that he was pleased to know that I had done what he asked me to do. And so it's kind of, I reacted positively. My brother reacted negatively to the same inputs. But anyway, so I'm in favor of not procrastinating. Get it done early. And I know people who say, oh, I do my best work when I'm under pressure. And I think that's just absolute fallacy, okay? I don't think anyone does their best work when they don't have time to do a good job, okay? I think that's an oxymoron. But anyway, that's another story. Okay, let's talk a little bit about the presentations. Are we on? Okay. So on the presentations, the presentation should be limited in scope. I don't want you to come in and spend 10 minutes telling us how to solve world hunger. I don't think that's really going to be enlightening for anybody. I mean, you can get those types of stories out of the Wall Street Journal, okay? And they're worthless. They're not worth reading. In fact, I did give a couple of B's last year because the people came in and gave me stories, right? In fact, one of them did a story and just paraphrased what they read in the New York Times about composites and ultra-lightweight composites in Boeing aircraft. And at the end of the story, they sort of admitted they would never use these ultra-lightweight composites because A, they were too expensive and they had no structural integrity. I mean, they were so lightweight that they just collapsed, okay? Things like aerogels, okay, if you know what an aerogel is, okay? It's got a density half that of water, okay? And if you blow on it, it will collapse. It's sort of like you ever seen kids play with making bubbles, soap bubbles? It has about the structural integrity of a soap bubble. Put any stress on it, and it collapses, okay? And they came in and they told us this wonderful story about how aerogels were going to take over the world. This is an article from 15 years ago. I said, and so are they using them? Well, no, not yet. Okay. What do you mean, no, not yet? You just told us this was the material of the future, wonder material. I didn't say that to him in class, but I did give him a B. So I want something of substance. And I think that goes without saying. You're at MIT. I don't want it to be too general. For example, using my own talk yesterday about 3D printing, I didn't do 3D printing in general or additive manufacturing in general. I did 3D printing of metals. And if you actually went through the outline of what I did, I could have given you a PowerPoint presentation of that in 10 PowerPoints and, cover things like I could have done Prandtl number, Bond number, and what was my other dimensionless number? Anyway, whichever one it was, on one overhead, right? And said, these are the properties of metals. And talked about what are the limitations of doing 3D printing of metals. Okay, that's something of some substance that hopefully most of you didn't already know about, and so you learned something from it. And that's what I want from you. Okay, I took 50 minutes, but I'm the professor. I have a certain, literary license. No, actually, I had to explain a few things along the way. And when you're doing a presentation, you don't have to explain everything. That's what questions and answers for at the end. Okay, you're just trying to introduce the topic to somebody. Any questions on that? So don't tell me about use of composites in automobiles. That's a little broad, okay? If you want to say use of aluminum silicon carbide calipers for lightweight brake linings for disc brakes, okay, great. That's specific enough. And I'm sure you can get down to why they do them, why they do it, or why they don't do it. That is actually an example from 25 years ago. People were all excited about using aluminum silicon carbide composites for brake calipers, and they found everything was fine until you hit the brakes very hard. The aluminum heated up and crept, and all of a sudden your calipers no longer had the same shape, and they wouldn't squeeze the brakes anymore. Minor problem, called brake fade. You know, hit your brakes hard 3 times in a row, and you have no brakes. And you never will have brakes. You're going to have to replace your brakes because they just deformed out of shape. Anyway, so little things like that. And actually, if I'll remember and I have time each day, I will try to give you my sound bites from the day before. Here are my sound bites from the day before. I wouldn't have expected any of you to be able to generalize where I talked about 3D printing to come up with these types of things. But one of them is material selection, which is what this module is supposed to be, is a multi-dimensional problem, okay? You know, people say, well, why don't you just do 3D printing of metals? Well, there's quite a few reasons, and I spent a whole hour going through a lot of the reasons, and hopefully you realize it's a more complex problem than you just substitute plastic for metal in your 3D print head, okay? It's more complex. And it involves mechanical and melting problems, and I've organized it in that way and stuff. So it's multi-dimensional problems. Most things we're going to talk about in material selection are multi-dimensional. Okay, you can use a material, dig it out of the ground. Sometimes the biggest problem is recycling it. Okay, for example, and people don't always think about that. We also talked about Ashby plots, and Ashby plots basically tell us there are limits to material properties. You can't just, you know, we'd love to have a material that has a strength of 5 million psi. Anybody know why we can't do that? We can't do it, by the way. The strongest material we can get is about 3 million psi, and that has to do with the strength of the individual chemical bonds. Okay? If you take, what's the strongest bond in the world? All you chemists out there? None of you are chemists, so it's okay to answer. Guess. Most people will say carbon-carbon because that's what we have in diamond, which is the strongest material. It's not the strongest bond. Strongest bond, if you're a chemist, is silicon-oxygen-silicon. Silicone bond. Okay? I actually told you that yesterday, but you didn't remember it because I told you that silicone rubber had the highest melting temperature of any of the rubbers, 500 degrees. And it's because that backbone of silicon-oxygen-silicon, as opposed to the Kevlar backbone of carbon, 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 the silicone backbone is actually stronger than the carbon-carbon bond. And if you actually calculate what the strength of that bond is going to be, you'll get about 3 million psi. And you know about this because you've read in the New York Times and the Wall Street Journal all about carbon nanotubes, right? And they have a strength of 3 million psi. Well, that's a calculation that was done in the 1930s when we first learned quantum mechanics. And they actually learned something about the bond energy. And I think if you take my solid-state welding course, I spend half a lecture going through this type of stuff. But basically, we're limited in our material properties by the strength of the chemical bonds between the atoms. Okay? There's a fundamental limitation. You can't get a material with a modulus higher than 60 million psi. I can't remember, what's that, 200? It's not 200 gigapascals, about 400 gigapascals if you're a metric. Whatever it is, but that's limited by the strength of the chemical bond. Unless you come up with some new elements that have stronger bonds, we're not going to get anything any stronger. And what's the problem with the 3 million psi of carbon nanotubes? Anybody know? Actually, I told you that yesterday. It's the fact that we have defects. I told you about fracture mechanics and Griffith, and little notches can weaken the strength of things. Well, I think I told you the Bob Sprague quote about material scientists know that it's defects that control properties. Okay? And a perfect carbon nanotube would have a strength of 3 million psi. But does anyone in here know of anyone who's ever measured that? Well, how do you grip a little carbon nanotube to measure the tensile strength? And if you did, you would find it probably has about 1/10 of that strength. And the reason is there'll be vacancies in there. In that perfect little carbon nanotube, there's going to be a missing carbon atom. Any temperature above absolute zero, thermodynamics tells us, entropy tells us, that we're going to have a vacancy. And if you have a vacancy, that's a defect in that carbon nanotube. And that will create a stress concentration, and it will be much weaker, maybe 10 times weaker. So all of you that are out there working on carbon nanotubes for structural applications, you'll get a thesis out of it. You just won't get a useful product, okay? Because we've known these things for 60 years. But some physicist down at Rice University, who thought he should win the Nobel Prize, actually I think he did, for discovering buckyballs, did the calculation that had been done in the 1930s, and he took credit for saying, I've discovered a new material that is going to be 10 times stronger than anything else we have. Well, you know, in the 1940s, we actually measured iron whiskers that had a strength of 2.2 million psi. And we got around the defects of the dislocations because the iron whisker was a single crystal with a screw dislocation right down the axis. And so when you pulled on it, there was no stress on the dislocation, if you know anything about dislocations and Berger's vectors and things like that. And you got 2.2 million psi. A student about 20 years ago said, well, how do you do that calculation? And I'd explained how you would do it. And then they kind of challenged me, so I went back to my office, and 5 minutes later I'd scratched it out. I got 2.2 million psi for the strength of iron. It's just the strength of the chemical bond between two iron atoms. It's a calculation that was done 90 years ago, but this guy 20 years ago discovers buckyballs and wins the Nobel Prize because he goes around in the press, I've discovered a new material that's going to revolutionize the world. Okay, he discovered those 20, 25 years ago. Have buckyballs revolutionized your world in the last 20, 25 years? Don't think so, okay? But actually it has, for all of you that are doing research. There's lots of research money to study this. Anyway, so there are limits to material properties, and we're going to talk about those limits in some more detail, okay? So that's a summary, and now I've gone through 25% of this lecture just summarizing the last lecture, but hopefully pointing out some other things. I did want to finish up this stuff on why we don't do 3D printing of metals, and here is, I will pass this one around from Dr. Belmar, which is this $500 part, laser printed. I'm sure it took hours. He didn't know how long, but I'm sure just knowing the solidification process of thin layers, that probably took hours to produce that. And that's why it costs $500. So you can 3D print metals. Not very economically, but you can do it. And if you're talking about something that's going to go in outer space, that's great. And I told you about things. We were trying to make propellers for the Navy so they wouldn't have to buy castings and let them sit in a warehouse for a year in case their propeller broke. We tried to do some stainless steel just because it was easy. We were doing simple geometries. And what happened, I told you about the surface tension problems. And what happened here, you can see on the edge, we started to get some imperfect melting, and the defect propagated and got larger and larger and larger because of the surface tension. Okay? You can see the first part of it gets a little wavy, but it didn't look too bad. But all of that is due to the surface tension of metals, which are 10 times higher than the surface tension of other materials. I don't think, did I pass this one around? This was the Inconel, I think I may have passed this one around. This is the Inconel 100. It's actually a pretty good deposit. You'll see some little humps on either end because you scan this way and you start scanning back that way, and there's a delay as you go from a finite velocity in that direction, and then you have to accelerate in the other direction, and so you actually build up a little more material on each end, and that's just because of Isaac Newton, and you can't make an infinite change in speed. But to answer this question of why, yeah.
So this was 3D metal printed?
Yep, it's just a wire of manganese, aluminum, bronze, welding wire. It's a tube. I think that might be a manganese and aluminum bronze tube, and we just went around in circles. Okay? Now we did it with an electron beam for reasons of the Fourier number and the high heat transfer coefficient you need to solidified metals, okay? And the manganese aluminum bronze actually has a better wetting surface tension balance than some of these other things. You can see we were reasonably successful with that. Although we're going to still end up with tremendous residual stresses. Does that answer the question? Okay, so yeah, it's just a fairly simple process. So I was now going to tell you the question that was posed to me by Technology Review editor was, why don't we do the 3D printing of metals? And at the end of my spending an hour with them, I said, but in fact we do, and we have been for 80 years. Okay, for example, the US Air Force, about 25 years ago, decided they need to rebuild the tips of turbine vanes. And these turbine vanes, which go in a jet engine, basically are spinning around, and they get hot with time, and they creep and get a little longer, and so they wear out the edge, the top edge. They want to rebuild them. The thing is still good for another 3,000 hours of use, so they built a little machine, a little arc welding machine. They called it the dabber, and they would build up the edge and grow. They would machine it back, and they would redo the edge, and then they'd remachine it. Well, when you're talking about a vane that might be worth $500, you can afford to spend a couple $100 to repair it if you're going to have a brand new vane, right? So high value added part, high heat intensity, very limited geometry. I don't have one, but I've seen these things where they grew a thin vane like this. I've got 2 different sizes by an extra 1/4 of an inch, and then remachined it. And it's not critical. There's not a lot of stress on it in service because it's the tip. It's the big stresses are down at the base where you have the biggest centrifugal forces. The tip doesn't have big centrifugal forces. So there's an example of something. The Air Force automated it in their Oklahoma City repair facility as a $10 million machine to do it. Because to have all that precise alignment and control and everything else costs money. But they were going to make $50 million worth of blades on a $10 million machine. You could amortize it. Okay? So we have not solved the problem of 3D printing of printed circuit boards, but we have done things for 80 years. There's a $1 billion industry out there called thermal spraying, where we repair old worn-out parts. Companies like Eutectic Castellan is a $400 or $500 million a year company, and they make all kinds of metal powders, and they put them in a flame, and you take a piece of metal and you flame spray, you thermal spray this powder on top of the metal. You might melt it, in which case you probably are going to have to preheat that thing to a very high temperature, okay, because of some of the things we talked about. But they've been doing weld repair, basically thermal spray repair of parts for 80 or 90 years. Usually nice circular parts or flat parts, not complex geometries like 3D printing, but we have been building things up by additive manufacturing for years and years. Visited POSCO Steel when it was the largest steel company in the world, one of the largest steel plants in the world in Pohang, Korea. They took me through a facility where they refurbished the rolls for the continuous caster of the steel mill. These rolls are about 12 feet long, about 1 foot in diameter. A molten band of hot steel comes down out of the casting machine, which is about 7 or 8 stories tall, and it gets bent 90 degrees. And these rolls, and there are hundreds of them, are bending this hot steel. Well, they wear out. I mean, they're touching steel that's at above 1,000 degrees centigrade, and there's a lot of wear. Rather than throw out these rolls, which are actually water-cooled in service, but the surface is touching something that's basically 1,200 degrees centigrade, they'll get thermal cracking on the surface and things. So they'll take them into the shop, and this shop was about half the size of a football field, okay? And they just had lots of lathes. They'd have this 12-foot-long roll, and they'd do a pass, and they'd cut off the bad stuff on the surface, and then they would preheat the whole thing. I mean, there were flames all over this shop. I think I was there in August, and it was pretty hot, okay? And just great big flames, preheating these things to 600, 700, 800 degrees Fahrenheit, and then just laying down weld metal. They got around the residual stresses because they're welding and with the flame temperatures, they're stress relieving as they go. But they're building up, 2 inches of metal on the outside of these rolls. But they got to replace these rolls periodically, probably after 2 weeks of service. And this machine is going to run continuously for 2 or 3 years. Okay, so you have to replace them in situ and stuff. Hey, we do lots of buildup of metal parts. There was another example I was thinking of. Another fancier turbine blades, not those, but the ones that are in the hot section of the engine. I've been to places where they're doing electron beam, adding the tip or something, melting in there, and they're preheating to 1,000 degrees centigrade, 1,800 degrees Fahrenheit, because of this problem of sucking out the heat and the fact that the alloy is a nickel-based superalloy and is very prone to cracking. And so if you have big thermal stresses, you're going to get cracks. So what do? They preheat it up to within a couple hundred degrees of the melting point. Okay? So we do it. Just it's a little tricky. And it's a little bit expensive. And you don't do this on 20-cent a pound parts. Okay? You do it on very high value added parts. So 3D printing is a wonderful technology. Nanotechnology is a technology. I won't use the word wonderful with it, but it's a technology that is oversold. So let's start after 2.5 hours. Start actually talking about what we're going to do in this course. Lecture 1, which we'll start today, is on externalities. And then we'll go to price, cost, and abundance and talk about limits of properties, which we've already talked about. We're going to talk about materials manufacturing, productivity. We're going to spend a fair amount of time talking about productivity of different materials, steel, aluminum, composites. You're going to hear the word steel a lot in this course. In fact, usually the students, after about 2 or 3 days of lectures, will start making jokes about all he ever talks about is steel. Well, you're going to find out why in a little bit. There's going to be some statistics on steel that will probably surprise you. Nonetheless, let's talk about productivity and competitiveness. Does anyone know the difference between productivity and competitiveness? I'm going to make this an economics course here. Yeah.
I guess competitiveness is relative.
Exactly. Yep. It's relative, and it involves things like price of labor in one country versus another, right? Productivity is how well can you make something? And it's sort of independent of things like labor rates, yen-dollar exchange, yuan-dollar exchange. Those exchange rates are all part of competitiveness. Can the Japanese make something cheaper than the Americans? Can the Indians make something cheaper than the Americans? Okay? At equal quality or whatever. Okay? Competitiveness is a huge, all-encompassing issue. Productivity is how efficiently can you manufacture it? Usually measured in person hours per ton, person hours per gram, whatever. Okay? Some amount of effort divided by a quantity. Okay? Now it turns out back before you were born, in the mid-1980s, the Japanese were eating our lunch. Okay? Something like 75% of Japan's workforce was involved in something that had to do with exporting, and the Japanese were selling Toyotas here that were better quality than any of the GM junk that they were producing then. GM's improved significantly. And there are a number of books that were written about this. One of them was what's his name? Dan Roos's book. He was the second author. But a book called Lean Manufacturing. You've all heard about lean manufacturing. Term coined by a professor in civil engineering here who was an expert in the automotive industry. Okay, I remember Dan Roos 20 years ago was personal friends with the CEO of every major automotive company in the world. Okay, he was sort of a specialist on automotive manufacturer. And he did a study of why Toyota was eating our lunch. And he pointed out they were using lean manufacturing production technologies, which is now a very common, very big buzzword, but in the mid-1980s it wasn't. In the meantime, mid-1980s, I was a young professor. I probably wasn't even a full professor at the time. And a guy named Jerry Wilson was the dean of engineering, and he was very concerned about the declining productivity of the American industrial sector. And people were looking at the amount of employment in manufacturing in the United States, and it was just decreasing. Back in the 1980, it might have been over 20% of the workforce in the United States was employed in manufacturing. High-value jobs, United Auto Workers. These people made enough money to be able to buy a home and a car and send their kids to college and things like that. And the workforce was decreasing, okay? It turns out there was a guy at General Motors who was the vice president. He was very big on robotics. He was going to eliminate all the hourly workers at General Motors, okay? He didn't like General Motors always despised the hourly workers. And it was sort of a mutual distrust between the two. And they had terrible labor fights and whatnot. These are some of the externalities that go on. And it turns out this guy, he used to, this is before we had PowerPoint and all these other things. I used to see some of his presentations. He would have $50,000 audiovisual presentations on what General Motors was doing with laser manufacturing and things like this. Turns out during the decade of the 1980s, General Motors spent $50 billion automating their manufacturing facilities, okay? Did you know that in the 1980s, if it had been legal in Japan to purchase Toyota on the stock market for a foreign company, General Motors could have purchased Toyota for $50 billion, okay? But they couldn't because the Japanese laws, that's another externality. Japanese laws wouldn't allow an American company to go purchase stock of a Japanese company in Tokyo, or in Japan. Anyway, the Japanese were eating our lunch. And so Jerry Wilson commissioned a book that was written by Michael Dertouzos, who was head of CSAIL, Computer Science Lab, almost became president of MIT. Michael's passed away now, but he was a Greek. He was a consultant to the premier of Greece. I remember Michael, they were complaining at Engineering Council once about the assistant professors didn't make enough money to live on in the Boston area. And he said, well, let them go out and consult. They can make $20,000 a day. I said, what? Well, that's what, Michael was making that kind of money, okay, as a consultant, consulting for the government of Greece. Richard Lester is still around. Bob Solow won the Nobel Prize in economics. Anyway, these guys were asked to be part of a commission, MIT Commission on Industrial Productivity in the mid-'80s, and which they did. And they wrote this book. I was a commission member and did something on steel, productivity in the steel industry. And this is the opening part of the book. And I've highlighted the first sentence. To live well, a nation must produce well. And that's what the whole book was about. Why was the United States not as productive as Japan, okay, in manufacturing? Well, I had spent my sabbatical in 1984 and 85 in Japan. I had walked around these factories and these research labs, and they certainly didn't seem like they were as productive as the American factories that I went through. And it turns out they weren't. They were more competitive because at the time, the yen-dollar exchange, when I was renting my home in Tokyo, the exchange rate was 240 yen to the dollar. What is it today? Anybody know? It's about 100 yen to the dollar. So what had happened in the 1980s is the Japanese, the Toyota wanted to sell in the United States because we were the world's market. We were 1/3 of the world's gross domestic product. Everybody wanted to sell in the United States, so Toyota was manufacturing cars in Japan. They were doing a wonderful job of manufacturing, lean production, and they were shipping them to the United States. And Ronald Reagan, in the meantime, was doing Star Wars. He was going to defeat the Soviet Union, and he did. He defeated them economically by bankrupting them. They couldn't keep up with all the money we were spending on Star Wars. Star Wars was a big defense initiative, right? And eventually the Soviet Union fell apart in the early 1990s for economic reasons. In any case, the Japanese were loaning us money, and we were running huge deficits in the federal budget that we had never run before, because Ronald Reagan was going to defeat the Soviets, he was going to outspend them, and he did, and the Japanese were loaning us money at 240 yen to the dollar, so we could purchase their Toyotas. And we did. And there were better cars than General Motors, and there was a big upheaval, and it turns out eventually we had to pay the piper. And we are now paying the Japanese back at 100 yen to the dollar. So we're taking our 60% discount because the Japanese thought they could just suck up those dollars and keep on hoarding dollars, and except it doesn't work that way. There's another country that's doing that right now. What's that country? No one knows? Who's doing all the manufacturing in the world? Where everything you get says made in China. And anybody heard anything fights about the yen, the yuan dollar exchange rate? And it turns out the Chinese have trillions of dollars. Trillions of dollars. And now they're finding you can't eat dollars, okay? You might be able to buy something with dollars, but they just don't taste good, okay, those dollars. And so now, eventually, they're going to have to let the yuan float in the international currency, and we will be paying the Chinese back all these cheap VCRs and all these things we've been buying from them. We're gonna pay them back 20 cents on the dollar, okay? And they're not going to be happy about it, to get 20 cents on the dollar for the trillions of dollars worth of goods they manufactured and sold us, okay? There's only one country in the world that can do this. It's the country that's currency is the market for energy. The price of oil is denominated in dollars around the whole world. Whoever controls the dollar is defining the world's currency. And everyone else has to adjust to we're the reference point. Okay, and you're seeing this right now. Europe's being the European currencies are being devalued with regard to the dollar. Why? Well, it turns out to live well, a nation must produce well. Which country has had the highest manufacturing productivity rate for the last 100 years? The United States. We are the most efficient producers. Even in the 1980s, when we were buying Toyotas to build Star Wars and to buy the Toyotas, and the Japanese were loaning us the money to do it, we still had better productivity. And why were we building Star Wars and the Japanese were building cars and someone else in Taiwan was building whisk brooms or whatever? Anybody know the economic principle behind that? It's called the law of comparative advantage. If we both can make something, let's say we can both make a computer, but I can make it faster and more productively, less cost, than you can make it, but if I can actually make the computer chip better than you can, and comparatively 5 times better, I can make the computer chip, I'll let you assemble the computers. We can both do it, I could do it, but I'd rather get the comparative advantage of making the high-value part, the chip that goes in it. Or I like to be Boeing. I like to get the high value of assembling and designing the aircraft. And I'll let you build some components that I'll stick on in my factory, but the law of comparative advantage is I'm going to take the high value stuff, I'm going to leave you the lower value stuff. If you take an economics course, it's the law of comparative advantage. We have the highest productivity in the world, and we always have for the last 100 years. Now, we stole it from the British, who had it in the Industrial Revolution, okay? But we have the highest manufacturing productivity. Why has manufacturing employment been going down for the last 50 years in the United States? Because our productivity has been going up. Everybody thinks, because if you read the Wall Street Journal, we're losing our manufacturing competitiveness. All the jobs are going offshore. The jobs we don't want are going offshore. We're exporting our pollution. Let the Chinese make the stuff that pollutes. We want to have nice, pretty views. We want to walk through clean air. We'll let them choke on their smog. Okay? This is what we do because we have been the world's dominant productivity king for a century. And the world buys its energy, and energy is the thing that determines the cost of things in general, in dollars. And whoever has the gold rules, okay, the golden rule, we have the dollar. And as long as we keep our productivity up, I actually used to give a talk on this. At the time of the American Revolution and the Constitution and George Washington, anybody have any idea how many people were involved? What fraction of the workforce was involved in agriculture in 1790? 97%. 97 people out of 100 were just toiling away to make food. And 97% of them, they made enough extra that 3% of the people could be George Washington or Thomas Jefferson or Ben Franklin. But those people were in the minority. Today, well, actually, if I went back to 1980, how many people, what fraction of the United States population was working in food production in 1980? 3%. We had a 30-fold improvement in 200 years in productivity in food production, which is a pretty basic need, okay? What fraction is it today? It's about 1.5%. We're losing those farm jobs. Haven't you read that in the Wall Street Journal? Right? Rural America, they're all moving to the cities. Why? Because the law of comparative advantage says, hey, you might have been able to live for free on the family farm, but you can come here and pay $2,500 a month for a 2-room apartment, right? That's productivity. No, that's competitiveness. But in any case, to live well, a nation must produce well is the beginning of Made in America. And is Paul Krugman. Who's Paul Krugman? He's an economist. He started at MIT, went to Stanford, won the Nobel Prize. Now he's at Princeton. Okay, another one of these people that Lester Thoreau was talking about. They tend to hire our extinct volcanoes. But as Paul Krugman says, he's right. Productivity isn't everything, but in the long run, it's nearly everything. Okay? So what are the things that determine productivity in material selection and economics and stuff? Well, they're externalities. Anyone taking an economics course, anyone know what an externality is? Oh, okay. An externality, right out of Wikipedia, which is the source of all knowledge, right? What did I do here? Oh, that's not it. I have to figure out. Anyway, I'll just have to read it without blowing it up. In economics, an externality is the cost or benefit that affects a party who did not choose to incur that cost or benefit, okay? Something external, like air pollution, okay? All the rest of us have to endure air pollution because someone designed and built these trucks that are dirty. Let's see if I can figure out. Well, let's not worry about it. So the externalities, there are lots of different types of externalities, and let's talk about some of those. Political. There are political externalities, rare earth metals. What's the story with rare earth metals? What's the political externality of the last 8 years? What happened on rare earth metals, and why are rare earth metals important? Yeah, Brandon.
Rare earth metals are used in battery technologies, and many technologies. They're very dirty, and several countries have produced the majority of the rare earth metals, and they use very toxic
Production methods. We export our pollution, right, to let someone else breathe that air. Okay, rare earth metals. You ever heard of neodymium iron boron magnets? Neodymium is a rare earth metal. Okay, samarium cobalt are magnets. Rare earth metals are functional materials, not really structural materials, but functional materials used in many high-value applications. And no one remembers, well, maybe you were in elementary school at the time, but about 8 years ago or so, turns out China has tremendous rare earth metal reserves. Now, they're not really that rare. It's a misnomer. The United States has tremendous reserves of rare earth metals too, but China has lots of rare earth ores, and it is a very dirty process. You think you're in the black hole of Calcutta, okay, to go see a rare earth metal plant. People die at an early age who do this because they do it by technology that's 100 years old. In any case, the Chinese had dropped the price because of the law of comparative advantage. We had produced rare earth metals back in the 1970s and 1980s, but the Chinese, as China opened up, after Richard Nixon opened up China, the Chinese decided they had all these reserves of rare earth metals, they had cheap labor, they weren't worried about the pollution at the time, and they could produce rare earth metals and sell them cheaper than anybody else. So all the American mines and factories shut down because of the dirty industry, and they're going to get fined by the EPA anyway, so send it to China. Let it go to China. And the Chinese, all of a sudden, they're producing like 90% of the world's rare earth metals. And they decided they were having a fight with Japan. And who needs all these rare earth metals in their magnets and their batteries and things? The Japanese, for their consumer electronics. It's replaced automobiles as one of the big high-value export industries in Japan. And so the Chinese just decided, we're going to put an embargo on, and we're not going to ship you any rare earth metals. And the Japanese government and the companies went berserk. They were going to be shut down because they couldn't get this critical material. It wasn't rare, but it turns out the Chinese had a de facto monopoly because everyone else had gotten out of the business. So for the last 6 or 7 years, half the faculty at MIT that are working on materials are dabbling in some way to produce rare earth metals by a clean technology, so that the next time the Chinese pull this stunt, okay, we'll be ready to come in and do something. Same thing happened in 1973 with the Arab oil embargo. We were all buying $2 a barrel gasoline, oil. Crude oil was being pumped out of Saudi Arabia for $2 a barrel in 1972. And all of a sudden the Arabs got together and they said, we're not going to ship you any more crude oil. And all of a sudden the world economy came to a screeching halt in many areas. The price of energy shot up. There was the oil crisis, we called it. My wife and I and everybody else would sit in line for 4 or 5 hours waiting to fill up our gas tank. So all these cars are running their engine, sitting there in lines that are 100 yards long to get up to the gas pump. Okay? It's wonderful. Okay? Same thing happened. They tried it again in 1978. By 1978, it was nowhere near as effective, because all the American industry said, we're not going to let you do that to us again. We're going to be able to use natural gas or oil, and we'll just be able to flick a switch. American industry spent millions of dollars to be able to just flick a switch and change from firing those electrical plants with oil or gas. And so the next time they had an oil embargo, we'll just switch to gas. Price of gas went up, price of oil went up, but nowhere big as a disruption as it had been in 1973. Okay? Tried it again in 1982, wasn't so effective. And now, 40 years later, Saudi Arabia has decided they didn't like all the other oil cartel folks cheating on them, because Saudi Arabia can pump 12 million barrels a day at a production cost of $5 a barrel, and they were selling at $100 a barrel. They were very wealthy. Well, now they decided we're not going to keep losing market share. They were at 9 or 10 million barrels a day, and every time they had a little price increase in oil or whatever, or glut of oil, the Saudis would lose market share because Nigeria would just keep pumping. They're corrupt in Nigeria, one of the most corrupt countries in the world, and they would just keep pumping. They would violate all the cartel quotas, and they would, because their production cost is about $90 a barrel. And finally, Saudi Arabia says, we're going to shut down those frackers in the United States, and we're going to put Nigeria out of business because they've been cheating on us for the last 30 years. We can keep pumping oil all the way down to $5 a barrel and make money. Nigeria, they're hemorrhaging in Nigeria now. At $90 a barrel with a price of $30 a barrel, how'd you like to be in Nigeria right now? Okay? All those sins of the past are coming back. But we're sitting there, and it turns out anybody know what our fracker's marginal production cost is? The marginal cost, once you've already drilled the well and everything else, is down slightly less than $30 a barrel. So they can barely make it right now, but they can make it. They can't drill a lot of new wells, but the Saudis have not driven them out of business yet. They will eventually drive some of them out of business. But anyway, so their political externalities have nothing to do with the technology of buying a particular type of oil or product or whatever. Economic. I remember I had an explosion. Someone was welding on a oil storage tank in Oil City, Pennsylvania. Oil City's just down the river from Titusville. Anybody know what Titusville, Pennsylvania is famous for? It's where Edwin Drake discovered oil in 1857. Okay, he drilled for oil. Before that, the only oil anyone had was bubbling up out of the ground and up in the North Slope of Alaska, or the oil sands in Alberta. That's where oil is right on the surface. But Edwin Drake actually drilled for it. He found it rather than drilling for water. And they built a refinery there in around 1890s in Oil City, Pennsylvania. And they had an explosion. It killed someone. I had to go out there. And this was like 1995. And I go to Oil City. It's not the easiest place to get to. And the first day I'm there, it didn't make any sense. Old riveted 1920s storage tanks. The tank farm had about 2 or 3 inches of 2 or 3 feet of gravel. If you dug down about 1 foot, you'd strike oil, because for the last 100 years they've been spilling oil around the tank farm, and so the ground was saturated with oil. And I mean, the small production facilities, it's like a 30,000 gallon storage tank. Well, shoot, you go down to Houston, some refinery, and there's going to be a 100,000 gallon storage tank. Why were they? And that night I was sitting there thinking, why is Pennzoil keeping this plant running? Makes no sense economically. Well, it made perfect sense economically, and I figured it out the next morning at breakfast for myself. They couldn't afford to shut it. Because as long as they were operating, the EPA had no control over them, other than they could keep them from polluting anything off their premises. But the law is such that if you're an operating facility, the government is not going to touch those jobs. It's when you shut the plant that the EPA comes in and you're no longer protecting jobs. They will come in and they will assess you billions of dollars in cleanup costs. So Pennzoil was keeping this inefficient refinery operating in 1995 because they couldn't afford to shut it. Okay? It was a money loser, but if they shut it and put all these people out of work, it would be a humongous money loser. because the EPA would make them clean it up. Now, since then, they have shut it. It's too inefficient, and they do have to clean it up, and they're cleaning it up. But the rules have changed over the years. Do you know how they used to get the oil from Titusville, which was just up the river, down to Oil City? Just floated it on the river and skimmed it off at the other end. Okay. Nowadays, you see an oil sheen on the water, and the environmentalists are out there to put you in jail as a felon. Okay. But back in those days, there was no fish in that lake, in that river. Okay. They had all had oil for dinner. Okay, so Oil City, Pennsylvania, and Pennzoil. Sometimes the regulations will not let you choose the best material. Social, okay, social externalities. Lead. What do we know about lead? Well, Flint, Michigan is in the news, but lead is, I just had my house gutted. My wife and I rented a house down the street, 10 houses down, moved in October. We've lived in this other house for 37 years. Last week they came in to start the construction. You go through my house, you can see the studs, you can see the outside walls. I'm ripping out all the plumbing, all the wiring in this 90-year-old house. I'm going to rebuild it, okay? I wanted to get rid of the lead paint, okay? Because one of these days, that old house built in the 1930s, they're going to come by and I'll never be able to sell that house because it's got lead paint. And some environmentalist is going to say, you can't sell a house that has lead paint. Well, the rules were different in 1938, okay? But there's no lead paint in that house anymore. It's all in the dumpster, okay? Mercury. Mercury. Where's mercury used? It used to be used in lots of things, but there's mercury all over this room. Look at the fluorescent lights. Every one of them has an arc igniter that uses a little bit of mercury. And why can't you dispose of a fluorescent light in the regular old dumpster? Because it's got mercury in it. And so for environmental reasons, we try to get rid of mercury. Diamonds, okay? There's social reasons to diamonds, blood diamonds. I mean, they make movies about this stuff now, right? So there's all kinds of things. We're running out of time. I'll talk about some of the other externalities tomorrow. But there's all kinds of social